Welcome back, everyone. Today we are going over Chapter 10, which is correlation and regression. And remember, as always, so that you get credit for attending lecture, you must make sure you go to homework under My Stat Lab and look for today's lecture. Lecture for the assignment that I have here has Chapter 10 questions, which is what we're going over today. So in order to get credit for today's lecture, you need to make sure you're doing the problems that are assigned under homework. And today would be Lecture 23. Okay, so don't forget about that. I'll keep this open. I'll keep this here just, if we have time at the end, I just want to scroll through them. Just make sure I covered everything. Okay, and then of course the notes are under lecture notes. And I have the condensed version of the notes. So just so that you know you have the right notes here. You have to scroll all the way down, and it's hard to see on my copy or on my desktop here, but it's at the very bottom. So you have the condensed notes, and this is very condensed actually. But if you prefer to just follow along with my PowerPoint, I have another version of it, and it just takes it slide by slide. So that just takes it slide by slide. So it's the same information, it's just different formats. All right, so let's go ahead and get started. All right, so today we are looking at correlation and regression. So we're going to be exploring the relationship between two variables. Now we're only focusing on the linear relationship. So when I talk about a relationship, that is known as a correlation. So if I'm looking for a linear relationship, that's a linear correlation. All right, so that's what I try to underline here. Maybe I should box it. And so we're going to use sample data to make inferences about the linear correlation or the linear relationship between two variables. And when we use samples, we're making an inference about the population. Now, if there is a linear correlation or a linear relationship between the two variables, then we're going to come up with an equation that is used to make predictions about what's happening in your population. So if there happens to be a linear correlation between your two variables, then we're going to be using an equation to make predictions about what's happening in your population. All right, so we have something called the linear correlation coefficient, and that is R. So R is referred to as the linear correlation coefficient, and I'm circling it right here just because it kind of looks like it's part of the word coefficient, and it's not. So R is the linear correlation coefficient, and what R does is it measures the strength of your linear relationship. So R is the numerical measurement, and it measures the strength of your linear relationship between the two variables. Now, the variables we're looking at only represents quantitative data. So keep that in mind. The data we're going to be looking at is quantitative data. So it's going to be looking at the relationship between two variables, and the variables represent quantitative data. R is very important because R is going to measure the strength of our linear relationship. I'm trying to circle it. It's not working. There we go. Box it. All right, so that's R, and again, it measures the strength of our linear relationship or our linear correlation between the two variables. And of course, there is a formula for R, and we'll look at that. But there's also a way of finding R by using your calculator. All right, so let's go over some basic concepts. So we will see that a correlation exists between two variables when one of them is related to another in some way. In this chapter, we're only focusing on linear correlations. There might be some other type of correlation going on, but we're focusing on linear correlation. So R measures the strength of linear correlations and only linear correlations. And that's what I say again right here. Okay, so R measures the strength of linear relationships. So we're going to go ahead and look at some scatter plots. And scatter plots will tell us what's happening with our variables. Okay, so we're going to have two variables, and we're going to just go ahead and look at the relationship between our variables. And we do that by constructing a scatter plot. Okay, so I have a couple of pre-made scatter plots already here. And so what I want you to do is I want you to look at what's happening as you move from left to right. So if you're looking at this first scatter plot, you see that the points don't necessarily lie in a straight line, but they have a linear pattern. You do see a linear pattern, and what that means is as x increases, that's your horizontal axis. As your horizontal axis, as your values increase, so do the values on your vertical axis. So as x gets larger, so do the values on y. At least that is the trend. That's why you see a linear trend there. Okay, so the points don't necessarily lie in a straight line, but what you're looking at is you're looking to see what the trend is. And this seems to have a linear correlation between the two variables. So the variables we're looking at, it's a variable on the horizontal scale and the variable on the vertical scale. So x and y. As you move to the right, you notice that the points get closer and closer to be on a straight line. All right, and this one at the end has a perfect positive correlation. Look at the value of R as the points move so that they're closer to a perfect line. The largest value that R can equal is 1. So if all your points lie in a straight line, then you have a perfect correlation. This one, you see that the slope is positive, so we say it's a positive correlation. So it's a perfect positive correlation when R equals 1. Now 0.851, that correlation coefficient, it's closer to 1 than it is to 0. So that linear relationship looks like we do have a linear relationship there. But again, it's not as strong as when you move to the right. So the closer R is to 1, the stronger your positive correlation is going to be, the stronger your positive linear correlation is going to be. As R gets closer and closer to 1, the stronger your positive linear correlation is going to be. And look at the bottom ones here. You see that the slopes here would be negative. And look at what you would end up with if all of your points lie in that straight line. You have a perfect negative correlation because your slope would be negative here. So the smallest R can be is -1. The smallest R can be is -1. If R equals -1, you have a perfect negative correlation. Now the closer that R gets to -1, the better your negative correlation, the stronger your negative correlation. So remember, R measures the strength of your linear correlation. So again, as you move closer to -1, the stronger your linear negative correlation would be in this case. So we have our positive correlations and our negative correlations. All of these correlations are linear. R measures the strength of your linear correlation. All right, so let's look at this right here. There is no pattern on this graph. As you do have a scatter plot, there's actually, I don't see any correlation here. And so look at the value of R when you have no correlation. R is equal to 0. When you have no correlation, R is equal to 0. Now remember that R represents the strength of your linear correlation. So when R equals 0, that means you have no linear correlation. You also happen to have no correlation. There's no pattern here. But R measures the strength of your linear correlation, so there's no linear correlation here. Okay, over here there seems to be a correlation. It's just not linear. There's some type of quadratic correlation going on here that kind of looks like a parabola opening downward. There's a correlation here. There's a relationship, but it doesn't happen to be linear. So when R is close to 0, that means that the strength of your linear correlation is weak. So here R is pretty close to 0. It's a negative 0.087. I would say that's pretty close to 0. So when R is close to 0, that means you do not have a linear correlation. When R is very close to 0, that means that you do not have a linear relationship between those two variables. And even though there might be some other correlation or some other relationship, as was the case here, it doesn't happen to, it's not linear. So that's why R is close to 0, because R measures the strength of a linear relationship or linear correlation. All right, so let's go over let's summarize what we know about R, which is our linear correlation coefficient. So let's summarize what we know about R. All right, so one thing that I mentioned is that R takes on values between -1 and 1. So the closer R is to -1, the stronger your negative linear correlation is going to be. The closer R is to +1, the stronger your positive linear correlation is going to be. But if R is close to 0, that means that you do not have a linear correlation. If R is close to 0, that means you do not have a linear correlation or a linear relationship. Now, if you're working with, if your data is converted to a different scale, the value of R doesn't change if either of the variables is converted to a different scale. So maybe you're looking at kilograms instead of pounds. The value of R is not affected if your scale is different. Now, if you interchange X and Y, then again, the R is not affected. So if you're looking to see if there's a relationship between height and shoe size, well, it doesn't matter whether shoe size is the vertical or the horizontal axis. Your value of R is not going to change. It's not going to be affected. And again, R measures the strength of a linear relationship. Now there's one more thing that I did not put on this. It's on the notes, but it's not on here. It's on my condensed notes. And that is that R is very sensitive to outliers. The correlation coefficient is very, very sensitive to outliers. So that's one thing you want to add on to this. Let me go ahead and write it up at the top. Okay, so I typed it out. So the correlation coefficient R is very sensitive to outliers. So if you remember, an outlier is determined by calculating the IQR. So outliers, remember, anything that's above the third quartile by 1.5 of its IQR or anything that's below the first quartile by 1.5 of the IQR is considered to be an outlier. So the correlation coefficient R is very sensitive to outliers. Now, I was writing inside my text box, so hopefully that came out okay. When I wrote that out, it should say Q3 plus 1.5 IQR and Q1 minus 1.5 IQR. That's how you find out if you have an outlier. So if you happen to have outliers, first of all, you want to make sure they're not errors. If they're errors, then you get rid of them. But if you have outliers and they're not errors, then you want to consider what happens to your R with the outliers and what happens to the R without the outliers, and decide whether it's important to keep that outlier there or not. That's one of your questions for today's lecture assignment, is that it's asking you about this. So linear correlation coefficient is very sensitive to outliers. Okay, so I've been talking about this linear correlation coefficient R. And so here I show you the formula. So I've been talking about that correlation coefficient R. So here you see the formula. And this is something that you should already be comfortable with. You already know what the summation means. You know what N is. That's just our sample size. X are the data values for one variable, and Y, those are the data values for the other variable. So you already know what all this means. And it's a tedious calculation. If you want to just do it once, just so you know how to calculate the value of R. But I'm going to have you use your calculator to compute R. You're going to be using your calculator to compute R. I'm not going to ask you to compute it using the formula. All right, but that is how we calculate the linear correlation coefficient, which is measuring the strength of your linear relationship between your two variables, okay? All right, so if some of you are curious and you want to use the formula, you can use it once, see how it works, but I will have you use your calculator, okay? Now, when you're rounding the value of R, which is your correlation coefficient, you're going to round to 3 decimal places. Again, you're going to use your calculator to calculate R. Sound good? Okay. All right, so here's just some notation that you should be familiar with. The new one for you is at the bottom, so that's probably new. And in your sample, we use R to represent the linear correlation coefficient. That's what I've been talking about. But in your population, you use the Greek letter rho. So let me write it down so you know what I'm trying to say. So it's the Greek letter rho. So rho, it looks like a P here, but it's written and it's pronounced R, well, it's written as RHO. So that's your Greek letter rho. That's how you represent a linear correlation coefficient if you're talking about your population. All right, and so we do have our requirements, and of course we're only working with quantitative data. So the sample of paired data has to be a random sample of independent quantitative data. We're only looking at quantitative data. And again, you're going to have paired data. You first want to do a visual inspection or a visual examination of the behavior of your two variables by using a scatter plot. Okay, so first go ahead and construct a scatter plot, and I'll show you how to do that today. You're going to be constructing a scatter plot to see what kind of relationship those two variables have. If it's a linear relationship, then you continue to find what R equals, what your linear correlation coefficient is. If it happens to be a linear relationship, then you want to find out the strength of that linear relationship. But if it's not a linear relationship, then you stop. Now sometimes you're not sure. It may look linear, but it may not. Sometimes you're not sure. Then you continue to go find what R is. R measures the strength of that linear relationship. All right, so here I have an example for you. And so what we're going to do using our calculator is we are going to go ahead and graph to see if there is a linear relationship. And then we're going to find the linear correlation coefficient. Okay, so get your calculators ready. So right now you should see the calculator on your screen. All right, so when I changed screens, everything disappeared. So let me get my notes. All right, so the first thing you're going to do is you're going to go ahead and enter your data. And so you should, hopefully you remember how to enter data. You're going to go to Stat. And then you're going to go to Edit by pressing Enter. And you can just go ahead and enter your data there. Now I already have something there. I'm going to go ahead and clear it. That was from last time. So I go up to the name of the list, clear, come back down. I only do this because I like to work with L1, L2. But if you do not want to clear your lists, then you can just use L4, L5, some other lists that are clear. All right, so I'm just grabbing the notes because it all disappeared. I just have my data here. Okay, so it says that, and let me read the example again. A study compared the body weight and brain weight for a random sample of mammals. We are interested in estimating brain weight based on body weight. So we have to see if there's a linear relationship between the two variables. So what that means is as body weight increases, does the brain weight also increases? So do larger mammals have larger brains? Do smaller mammals have smaller brains? Is there a linear relationship between body weight and brain weight? Could we use body weight to help us predict brain weight? All right, so let's go ahead and enter. For my X, I'm going to, the body weight, that's going to go in for L1. So that's all I'm doing right now is I'm just entering the data. So as I'm entering, go ahead and do the same thing. Okay, so I entered my data, and what you have to do is you have to make sure that there are no mistakes that were made here. All right, so I'm going to check it one more time. All right, so I'm just checking to make sure that I have not made a mistake here. Okay, so I haven't found anything, so they look like they were entered. Okay, and that's one thing you have to make sure that you do not make a mistake when you're entering your data. If you make a mistake, there's no partial credit. Either you've entered the data correctly or you haven't. So when you calculate the value of R, using your calculator, you need to make sure you've entered your data correctly. All right, so it looks like everything's entered in there correctly. If you look at your notes, I at the bottom of the condensed notes, I tell you the command on the calculator that will give you the linear correlation coefficient R. There are a few, but the one that gets you all the information you'll need for this chapter is the linear regression t-test. So at this point, I'm going to go ahead and press STAT, S-T-A-T, there it is, STAT. Then I'm going to right arrow to tests. So using your right arrow key, I'm going to go ahead and press it twice, and then I have tests, and I have all my commands for tests. Okay, so I'm looking for the linear regression t-test. That's at the very, very bottom. So instead of scrolling down, I'm going to scroll up because that'll get me to the very bottom of my list. Either way you want to get there, just scroll and look for linear regression t-test. On my calculator, it's F, linear regression t-test. So when you select linear regression t-test, you're asked where the data is located. So the X's are in L1, and that's what I did, so I'm going to keep it like that. My Y's are in L2. Now if you put them in some other list, then you just have to change the name of the list. So you can just change the name of the list, wherever you put them. The frequency will stay as 1, and the inequality here, it will always be not equal to. Now I haven't gotten to the reason why it always has to be not equal to. We'll get to that before lecture's over. So I'll address that later. So for right now, just make sure you choose not equal to. And then skip over to where it says calculate, make sure that it's highlighted, and then you're just going to go ahead and press enter. So make sure your calculator that your screen is the same as what I have here. Again, make special note about where you put your X values and where you put your Y values. Make sure it matches up to the list that you've said they were in. I'm going to go over the word calculate and press enter, and we get a lot of information here. So right now I have to scroll all the way down to get what I need. And again, all this I'm going to use, but it'll be later. I haven't talked about it now, but what I need is at the very bottom. There's my value for R. So the value for R is the linear correlation coefficient, and it measures the strength of your linear relationship. Again, R is the linear correlation coefficient, and it measures the strength of your linear relationship. So there it is, it's 0.171. Okay, wow. Yeah, we rounded 3 places. Is that closer to 1 or 0? Yeah, that's closer to 0. So remember how I said I was going to graph it first, and then I got distracted, and I actually didn't graph it. I went ahead and I found R, which is what the example asked for. Yeah, that's pretty close to 0. So I'm wondering what my graph looks like. In any case, you always graph first, because sometimes you'll get a value of R that might be close to 1, and the relationship is not linear. So you have to really start with your graph. You have to make sure that the relationship is linear in order for you to continue. Okay? So in our case, R is not close to 1, so I'm pretty confident that the relationship isn't linear, but you always want to check your graph. Okay, so that's the value of R. You write it down somewhere. We're going to come back to it. So round it to 3 places. It's 0.171, so I wrote it down. Okay, so what I want to do is I want to look at the graph. That's what I should have done at the very beginning, looked at the graph. Okay, so to look at the graph, I am going to go to stat plot. Now stat plot is at the very top. It's right above where it says y equals. So second y equals gets you to your stat plots. And yours might all be turned off. One of my stat plots is turned on. So it doesn't matter which one you go to. I'm just going to go ahead and press enter. Once it's selected to the first stat plot, just press enter. And yours is probably on off, which it might look like that. So you want to make sure you just go to the word on and press enter. So make sure the word on is highlighted and press enter. And then make sure you select the first graph, which is a scatter plot. Make sure that your x's are where it says they are. Here it says my x's are in L1 and my y's are in L2. And they are, so I don't have to change anything. So make sure your screen looks just like what is here. And make special note about where your x's are and where your y's are. Make sure that you've indicated the list in which they're in. Now, the last option is to choose a mark, and it doesn't matter which mark you choose. I like to choose the larger marks just so that I could see it. I like to choose the larger marks just so that I could see them on my graph. Okay, now I do have my mic on, and I have here that the voice is coming through, but some of you can't hear me. All right, if you can hear me, can you just type out that you can hear me? All right, you can hear me now, but I did cut off. All right, so Jesse, are you okay now? Are you able to hear me? All right, so I did cut off. I'm not sure why. Maybe I was holding something I wasn't supposed to. All right, so let me just I'm just letting him know what he should do. All right, so the audio, if that ever happens to you, the audio is under Tools. All right. Okay, so everybody else can hear me. Okay, so that might just be for that individual. Okay, so make sure your calculator looks similar to what I have here on my window. Make sure your window looks the same. Okay, and the mark, it doesn't matter which mark you take. I usually select the larger one. Okay, so I'm good here. So the next thing I want to do is I want to make sure my window is set up correctly so it can pull up the data that we just entered. So you're going to go to Zoom. So I'm pointing to Zoom. All right, so I'm going to go to Zoom. So if you click on Zoom, I'm going to go ahead and select Zoom Stat. There it is, number 9, Zoom Stat. All right, so make sure everybody's goes to Zoom and then Zoom stat. Okay, I missed a question here, but Samantha, you answered it for me. Thank you. All right, yeah, the way that I got that window before, I did go to second and then y equals. Okay, so once you've set it up, you're going to go to Zoom now. There's my Zoom key, and then select Zoom stat. All right, so I'm going to go ahead and press enter, and there it is. There's my data. Okay, so yeah, it doesn't look like there's a linear relationship there, right? That's why the value of R is probably, it's closer to 0. The strength of that linear relationship, that's pretty weak. All right, so it doesn't look like a linear relationship. So you see that by making a scatter plot, you get an idea of what relationship you have or what correlation you have. But sometimes you're not sure. You're not sure if it's linear. This one, I feel pretty safe saying it's not. But I'm going to go through the process just so that you could see what you would do if there was a linear relationship. Here I'm pretty confident saying there isn't. And so you could go ahead and show me the correlation coefficient just to confirm what you're seeing here. And that's what we ended up getting. We got that value for R. It was 0.171. Okay? All right, so we're good. We graphed it. We also have the value of R. And that's what I'm going to write here. So by doing a linear regression t-test, a linear regression t-test, and that came from going to stat, and then we went to tests. I have a value of R of 0.171, and that did get rounded. Okay, so that's my linear correlation coefficient. This value of R measures the strength of the linear relationship. Notice that it's closer to 0 than it is to 1. So I do not have, it doesn't appear that I have a linear correlation between these two variables. It does not appear that I do. But I'm going to go through this process so that you could see the process. I'm going to continue through it. In any case, here it says we are interested in estimating brain weight based on body weight. Well, if there's no linear relationship, then I'm not going to be using that regression equation that I talked about earlier to make that prediction, because that regression equation can only be used if there's a linear relationship or a linear correlation. Okay, but I'm going to go through the process so that you see how we would work it out. Okay, so we have our value for R, which measures the strength of your linear relationship or your linear correlation. The way we interpret R, well, either you're using table A5, which is where your critical values are, or you're computing a p-value. So what we do is we go through a process of hypothesis testing. And in the traditional method of hypothesis testing, you're using critical values. So here our critical values are coming from table A5. And you would compare the value of R to your critical value from the table. Now, by using that linear regression t-test, some of you may have noticed that we had a p-value on there. So if you're using your calculator, you know if there's a significant linear correlation by looking at the p-value. And we'll talk about that later, about how we decide if there's a significant linear correlation or not. But there's two ways of finding out whether there's a significant linear correlation or not. Either you compare your R to the values in table A5, which are critical values, or you look at your calculator and you compare your p-value to alpha, which is your significance level. and make your conclusion that way. So you can kind of think about this as a traditional method of hypothesis testing using table A5. And if you have software, you're using the p-value method, or if you're using your calculator. But you can't just simply look at R and say there's a significant linear correlation. You have to compare it to something. You have to go through a process of hypothesis testing. All right. There is something else that you had, hopefully, when you looked at your calculator, you noticed that right above R, we had an R squared. And so that is called, we're going to explain our variations, called explained variation. The value of R squared is the proportion of the variation in Y that is explained by our linear relationship between the two variables. So it's just a proportion of the variation in Y that is explained by that relationship, that linear relationship between our two variables. So say that your R is 0.926, then that would mean that your R squared is 0.857. So R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. So if your R squared is 0.857, then what that means is that about 86% of the variation in Y can be explained by that linear relationship between X and Y. So you take that value and you turn it into a percent. And that is the percentage that we use. So in this case, it's about 86%. 86% of the variation in Y can be explained by the linear relationship from our two variables. And so what this says is that if only 86% of the variation is explained by that linear relationship, that means that 14% of the variation is not explained, cannot be explained by that linear relationship between X and Y. So R squared is the proportion of the variation, and that proportion is given to us as a percentage. So you can think of it as a percentage. It's the percentage of the variation in Y that can be explained by that linear relationship that we have between the two variables. All right, so here are some common errors that we run into when we're working with correlation. The first one is causation. So when we see that there's a linear correlation between two variables, that's all it means, that there is a relationship, there's a linear correlation between the two variables. It doesn't mean that one causes the other one to happen. So when we say there's a linear correlation or a linear relationship, that does not imply that one causes the other one to occur. So one does not cause the other one to occur. So it does not, you have to stay away from that. Okay, and then of course averages, if you're looking at averages, that suppresses individual variations. So that's going to change your value of R, your correlation coefficient. You have to be careful about that. We're looking at the actual data values. We're not looking at averages. And remember, we're only looking at linear relationship. We're only focusing on linear relationships or linear correlations. There may be other types of relationships that exist between X and Y, even if there's not a linear correlation. There might be other types of correlations, but we're only focusing on linear correlations. Okay, so the next part of today's lecture, we're looking to answer the question, is there a significant linear correlation? We want to determine whether there is a significant linear correlation between our two variables. You graph it to see if there is a linear correlation, because you can do a visual inspection. And if it's clearly not a linear correlation, if there's clearly not a linear pattern to what you're looking at, then you can stop there and just say that there isn't. If you're not sure, then go ahead and find R. So in our case, I went ahead and I found R anyway, and R was very close to 0. So that just confirmed what's happening in my graph. Now, if you want to find out if there's a significant linear correlation, you have to go through a formal hypothesis test. You can't just base it on your value for R. You have to go through a formal hypothesis test. So the setup for your hypothesis test is always going to be the same. Remember, the parameter in our population is rho. So the measurement of a correlation, of the linear correlation in a population, is rho. So that's why in our hypothesis, in our null and alternate hypothesis, that's what we see there. All right, so it's always going to be the setup where rho is 0 and rho is not 0. It's always going to be the setup. So remember, when R was close to 0 or equal to 0, that told us that there was there's no linear correlation. So remember, in our sample, when R was equal to 0, that means that there's no linear correlation. There's no linear correlation. So when we say that rho is equal to 0, the population linear correlation coefficient, when we say that the population linear correlation coefficient is 0, we're saying that there's no significant linear correlation. So you can write SLC for significant linear correlation. There's no SLC. However, if rho is something other than 0, then we would say that there is a significant linear correlation. So remember, again, in our sample, when we talked about the value of R, which measures the strength of our linear relationship or our linear correlation, when it was close to 0, that means we did not have a linear correlation. We did not have a linear relationship. All right, so we have to go through a hypothesis test, and there's two methods. There's two methods. All right, so I call this method 1. Your textbook does not refer to it as method 1, but I called it method 1. So if you're using method 1, your test statistic is going to be a t. When we did the linear regression t-test on our calculator, we have our test statistic there. It gave us our test statistic t. If you want to calculate it out using the formula, well, we have the formula there. You can get it from the calculator as well. All right, are you there? Okay, that was very strange. I don't know what happened. It looks like I lost my connection. Okay, thank you for Hanging in there. Okay, so it looks like it was fine on this last slide when I was talking about how we have to go through a formal hypothesis test to determine whether or not we have a significant linear correlation. Everything seemed to be okay on that slide. And then I think I lost my connection when I was talking about this one. All right, so one method for hypothesis test was the p-value method. And so the p-value method, you would follow this process. Your test statistic is t, and that is obtained from your calculator, or you could use the formula, but the t is given when you do the linear regression t-test. Your p-value is also given there. And remember, if you're using the p-value method, your p-value, if it's less than or equal to alpha, you're going to reject the null hypothesis. So what happens when you reject the null hypothesis? We are rejecting, let me point to it here, we are rejecting that there is no significant linear correlation. So if you reject the null hypothesis, then we believe the alternate, which says that there is a significant linear correlation. All right, and that's all this says right here. All right, so method number one is a process of hypothesis testing using the p-value method. That's how I've set it up here. So that's an option. Another option is that you use a traditional method of hypothesis testing, and this one uses your test statistic R. So the value of R that we got on our calculator, that becomes your test statistic. And remember, we rounded to 3 places. The reason we rounded to 3 places is because we actually compare that test statistic to values in table A5. And table A5 is in your pull-out formula card that came with your book, or it's in the e-book if you're using the e-book. So in this method of hypothesis testing, you're comparing your test statistic to your critical values. And if your test statistic falls in the critical region, you reject the null hypothesis. So we have 2 methods for doing hypothesis testing. And that's what I'm going to show you next. I'm going to go ahead and divide my screen into 2, and I'm going to use both methods. All right, so we'll do method 1 first, since we already have that from our calculator. All right, so we'll try to use different colors so you know which one's which. All right, so the question is there a significant linear correlation? So I'm trying to answer this question. Is there a significant linear correlation? So I have to go through a formal hypothesis test. We already have our value for R. That was from our last slide. I believe R was equal to 0.171. Now my guess is that there's not a significant linear correlation, because we already saw the graph, right? We've already seen the scatter plot. Okay, so I'm just going to go through the process so you know what the process looks like. So if you're trying to answer the question, is there a significant linear correlation? I am going to use method 1. So I go ahead and I set up my null and my alternate. So you need to make sure you're showing the steps. The parameter that we're talking about is rho. So in our population, rho is the linear correlation coefficient. It's R in our sample, it's rho in our population. When it's equal to 0, that means that there is no significant linear correlation. And I'm abbreviating that. The alternate is not equal to. So if rho is not equal to 0, you're saying that there is a significant linear correlation. So that setup doesn't change. It's always the same. Okay, our second step is our test statistic. So I'm going to put TS for my test statistic. And this is where you use the value of T. Now we already have this from our calculator, and let me show you what I have. So you're back to the calculator now. I'm going to quit. Second quit takes me back to my original screen. So I'm going to go through that linear regression t-test to get all that screen back. Okay, so I'm going to go to Stat, over to Tests, and then I'm going to scroll up so I can see the linear regression t-test. There it is, linear regression t-test. And then I'm going to press Enter. Now, it's just what I had before. I'm not making any changes. Everything's the same. So I go over the word calculate and I press Enter. I just had to do that again so I can get it back on my screen. All right, so at the very top, I have the value for my test statistic, and then right below I have my p-value. So that's what I'm looking at. All right, so if I go back to the whiteboard, you should see the calculator there. I'm just going to write on it. All right, so here we have our test statistic. I'm just copying it down. So t is equal to 0.426. 0.426. That's our t. We round it to 3 places because it's a t. And then our p-value is equal to 0.6852. So I'm just writing those down so I don't forget them. 0.6852. That's my p-value. All right, so now I know what my test statistic is here, so I'm going to go ahead and use it. So my test statistic is 0.426. My third step is to write down my p-value. And the p-value, that was 0.6852. 0.6852. Okay, so now I have to decide whether I reject the null hypothesis or fail to reject the null hypothesis. So remember, with the p-value method, you're comparing your p-value to alpha. Alpha's our significance level. So did I give you an alpha for this example? I didn't. So did you know what to use? Okay, so when I do not give you an alpha, whether it's in Chapter 8 or Chapter 9 or Chapter 10, you're always going to use 0.05. So write that down. If you didn't know that, make sure you make a note of that. So if alpha is not given, that's our significance level. Alpha is not given, so I'm going to use the default, which is 0.05. Okay, so what you're doing is you're comparing the p-value to alpha. If your p-value is less than alpha, then we reject the null hypothesis. If your p-value is less than alpha, then we reject the null hypothesis. All right, so alpha is 0.05, and my p-value is definitely not less than alpha, right? It's greater than alpha. So what are we doing to the null hypothesis? Okay, so we fail to reject, right? Our p-value is greater than alpha. Since our p-value is greater than alpha, we fail to reject. We fail to reject the null hypothesis. Okay, so that means I still believe the null hypothesis. I just failed to reject it. I still believe it. So I am going to put a blue box around it to remind me that I still believe the null hypothesis is true. We still have to assume it's true. Since I failed to reject the null hypothesis, we still assume it's true. And notice that on the side, I wrote down what it means to believe that the null hypothesis is true. So you want to make sure you have that as well. so you don't forget what it means. So if I'm still assuming the null hypothesis is true, it says that there's no significant linear correlation. And that's the fourth thing that you have to write in your process. So if we fail to reject the null hypothesis, there is no significant linear correlation here. There is no significant linear correlation between the two variables. All right, and we had already seen that in our graph, right? That's the first thing we did. We graphed, we saw the scatter plot, and it definitely was not a linear correlation going on between the two variables. And so this is our formal hypothesis test. You have to show me the steps, and at the end, you're saying, okay, you go through the process and say, no, there's definitely no significant linear correlation here. All right, so that's using method 1. And then I'm going to do the same thing, but now I'm using method 2. So I'm using a different color, so you just know that this is method 2. Okay, so for method 2, we have the setup is the same. It does not change. The setup does not change. So I'll say there's no significant linear correlation, and there's a significant linear correlation down here. Okay, step 2, in method 2, that means our test statistic is the value of R. R, which was our linear correlation coefficient. That was our 0.171. So you get to use that value of R. So no additional calculation there. You can just use the value of R. Step 3 is finding a critical value. And these critical values are found in table A5. All right, so let me bring that up so you know what I'm talking about. And just to remind you where I made that available, in case you haven't yet found it, it's in a couple of places. But if you're under lecture notes, I went ahead and put the formula card that I keep using. It's up at the very top. So if you click on that, the formula card comes up. And that's just the card that I had on my desktop. It might be a little bit different than the one you have with your book, but the tables are the same. All right, so where is table? Here it is, table A5. All right, so let's see if I can zoom in. Okay, not bad. There's table A5. All right, so do you remember what our value of n was here? So remember, we have paired data. So what did n equal? All right, so you guys see 7. All right, I don't know why I see 8. So let me check it. So here's 1, 2, 3, 4. So you guys agree? 8? Yes? Okay, good. I thought I was. All right. All right, so we have 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our sample size is 8. So we actually need that in our table. So alpha is 0.05 and then n equals 8. So when you look at the table, those are the things you're looking for. So n is 8, that's right here. And then alpha is 0.05, so that's your critical value right there. So 0.707. All right, so what I'm going to do is just to keep it the same, keeping it the same as what we've been doing in the past. When you look at the H1 says you have two tails. All right, so just like before, it's the same thing, two tails. And so 0.171 and negative 0.171. That's our critical value. And so you just have to compare your, oops, I wrote down the wrong one. That's not the critical value. I just realized it when I was putting it at the bottom. All right, what was our critical value? Do you remember? I circled it on the table. Okay, so I just corrected that. So that's the value that I circled on the table. That's what I should have written there. Okay, so that's our critical value. So look at our test statistic. So where does that test statistic lie with respect to the critical region? Is it in the shaded region or is it outside the shaded region? So then that should tell you what to do with the null hypothesis, right? So the test statistic lies, well, it's close to 0, right? So 0 is not in the shaded region. Do you see that? So R is 0.171. That's pretty close to 0. Okay, it's not in the shaded region. So we are going to fail to reject the null hypothesis. Now, is that the same result we had from method 1? So again, there's no significant linear correlation. Right, so you have your two methods, and notice that I showed the step, I showed all the steps. And so the question was, is there a significant linear correlation? And it wasn't just a yes or no question. I have to show why there is or why there isn't. And it's done through the a formal hypothesis test. Okay, now this is the data I started off with. Remember, we looked at the scatter plot and we said there's no linear correlation between these two variables. All right, so I'm not surprised that we ended up with this. This was what I was expecting. All right, so I continued because I wanted to show you the process. Okay, so in this case, we formally show why there's not a significant linear correlation. All right, so the next thing we're going to be looking at is we're going to be talking about regression. Okay, so we now know the relationship between the two variables. We looked at the graph, which was a scatter plot. We looked at the scatter plot. And the scatter plot tells us if there appears to be a linear correlation between the two variables. We found out that no, our example didn't look like a linear correlation. And we found the value R, which supported what was happening in the graph. It was close to 0, so there didn't seem to be a linear correlation between the two variables. Well, now what we're talking about is if there is a linear correlation between the two variables, there is an equation called the regression equation that is describing the relationship between those two variables. Now, this is only helpful if there's a linear relationship or a linear correlation. If a linear correlation exists, then we can use a regression equation to describe that relationship. So we are going to use the regression equation to make predictions about what's happening in our population. The straight line that goes through our points, and it's not going to go through every single point, but it's going to describe that relationship between the two variables. It's that line, that regression line, we're going to use its equation to make predictions. And so that's what we're going to focus on in this section. So the regression equation is that relationship between x and y. Now, x is called your independent variable, and y is your dependent variable. The equation, the typical equation of a straight line in algebra, you remember y equals mx plus b. That's how we used to write an equation of a straight line. And the slope was our slope was m, and our y-intercept was y. So we had the slope, which was m, and the y-intercept was y. Now in algebra, you remember that all of the points were on the line, and there's a formula for slope. Okay, for some reason that word slope doesn't want to, there we go. All right, so I couldn't get the L to stay on the whiteboard. So in algebra, we wrote our equations, our linear equations, as y equals mx plus b. M was the slope of your equation, and b was the y-intercept. And there was a nice little formula for our slope. It was the rise over the run. Okay, so it's the y's over the x's, y2 minus y1 over x2 minus x1. And if you had 2 points on the line, by using those 2 points, you can calculate the slope. Now, in real life, if we go ahead and plot our data, we're not going to get all our data points to be in a straight line. That's not going to happen. And so in statistics, we have a different formula for calculating the slope. And our equation of our line is different. It looks like this. It's y hat equals, the y-intercept is first, and the slope is second. So this time, the slope comes second. If you notice, you are always multiplying the slope to x. So no matter how you write it, the slope is always what's multiplying x. That's how you can remember what the slope is. It's always multiplying x. Now our y has a hat, it's y hat, so we are using it to make predictions. We're using what we know about our sample to make predictions about what's happening in our population. So this equation, this regression equation, is going to be used to make predictions. And in the calculator, so here's one other format of writing it. In the calculator, it gives it to you as a plus bx. Okay, so you just have to be aware of all these different formats. On the calculator, the equation looks like this. Y equals a plus bx. And again, the slope would be whatever's multiplying your x. That's your slope. All right, so again, this is just what I've already talked about, that regression equation algebraically describes the relationship between the two variables, and that regression line is the line on your graph that goes through the points. It's also called the line of best fit. And if you're looking at what the equation will look like, well, what you would have in your population and what you would have in your sample, those are the differences. So in your sample, you have one notation in your population, you have another one. So in your population, it's beta. Beta 0, beta 1. Okay, and these are the formulas. The formula for slope is right here. Very different than our formula for slope from algebra, right? Very different than when we used to find the slope of a line in an algebra class. All right, so that's the formula for slope. You're going to get this from your calculator. All right, the calculator gives this to you. And then the y-intercept, there's another formula for the y-intercept. Okay, so just in case you're curious, these are the formulas. If you want to use them, you can 1 or 2 times, but you're not going to have enough time on the final exam to be using these formulas. So you want to make sure you get comfortable with calculating all of this using your calculator. Okay, so the rounding of your slope and your y-intercept, it goes to 3 significant digits. And again, this formula is very important. Our regression line is the line that fits the sample points the best, and it's the y-hat. This is the equation to our regression line. That's called the regression equation. So we're going to use this regression equation to make predictions. We're going to use what we know from our sample to make predictions of what's going to happen in our population. So we're using this regression equation to make predictions. Now, we can only use it if there's a linear correlation. We can only use the regression equation if there's a significant linear correlation. So only if there's a linear correlation can we use this regression equation. If we do not have a linear correlation, then we use something else to make predictions. And that something else is the mean of the y's. So that regression equation isn't always helpful. If there's no significant linear correlation, we cannot use that regression equation. And that's the next example. Right there. All right, so now I'm asking you to find the best predicted brain weight for a mammal with a body weight of 83 kilograms. So we're interested in estimating brain weight. Now, brain weight, that was your y's. Brain weight, that was y's. Okay, so your brain weight, that's your y. So we want to find out what y is when you know the body weight, and the body weight, that was your x. So what does y equal when x is 83? So I need to make the prediction. So I'm going to go back to my calculator, and I'm just in case we can use it, I'm going back to write down the equation, the regression equation. So let me refer you back to the calculator. So on your screen right now, you should see your calculator. I haven't done anything to it. It's still where I want it to be. When we did that linear regression t-test, at the very top, you see the regression equation. It's y equals a plus bx. That's the way the calculator gives it to us. B is the slope. It multiplies x, so we know that's the slope. A is the y-intercept. So if you look at your screen, you may have to scroll down to see both of them. So A is 162.581, and B is 2.866, or I could say 2.86, yeah, 6 if I round it. So the slope and the y-intercept are given to you. So I'm going to just write that down just in case I need it. So let me take you back to the whiteboard. Okay, we might need that, so I'm going to just go ahead and write it out. So again, the calculator gives that to you as a plus bx. And then we have a, which is 2 point, no, A is 162. That's our y-intercept, 162.581. We're rounding to 3 significant digits. And our slope is 2.866. And that's multiplied to x. So that's our regression equation. So we have this equation, and we want to find out y when x is 83. Is it okay to plug 83 in for x to find y? Can I just take that and can I plug it in here so I can figure out what y equals? What do you think? Can I do that? All right, I have some no's and some yeses here. All right, so let's go back to the definition to see if we can do that. So it all comes back to this right here. All right, so when can we use our regression equation? Let's see if I did a good job in typing it out here. So if there's a linear correlation, the best predicted y value is found by substituting the x value into the regression equation. That's what this says. But that's only the case if there's a linear correlation. Now, I believe for our data, there was not a linear correlation. That's the one we've been working with, right? For our data, I believe there was not a significant linear correlation. So we have to go based on this part of our definition. So there is no significant linear correlation. So the best predicted y value is your y bar. All right, so how do I know that there was not a significant linear correlation? We had to do that hypothesis test, that formal hypothesis test. There it was. We went through our formal hypothesis test to find out if there was a significant linear correlation. And we saw that there is no significant linear correlation. There is no significant linear correlation. All right, so I can't do that. I can't use the regression equation here. The regression equation is only helpful if there's a significant linear correlation. Otherwise, I can't use it. All right, so I'm going to use a different color to do the rest. So I can't use that. It's not helpful here. So the best predicted value is the mean of your y's, and that's because there's no significant correlation. Since there's no significant linear correlation, I have to use the mean of the y's to predict. All right, so how do I find the mean of the y's? Here are my y values. How do I find the mean of the y's? All right, so you can do one bar stats, sure. You could do a 1-bar stats. If you didn't want to do a 1-bar stats, then you have all the y's. You could add them all up and divide by 8, right? Just to find the mean. But since we already have the data in our calculator, let's go ahead and bring that up again. So let me bring you back to the calculator. Let's go ahead and clear everything here. I don't think we need anything else there. All right, so I'm going to go to Stat and then select Calc, which is the second option there, using my right arrow key. And there's the 1-bar stats. You just have to remember where your y's are. I think I put my y's in L2. So second, and then the number 2. I think that's where it's at. The frequency just stays as blank. We only are interested in that one list of y's. And then over the word calculate, I'm pressing enter, and there it is. Okay, I don't see a y bar there. And that's what I'm looking for. So you have to remember that the calculator is always going to give you x bar. So you just have to remember that you entered the y's, and so your y bar is what the calculator is saying your x bar is. So the y bar is the mean up here. All right, so just keep in mind that you asked for the mean of all your y's. So the mean that's given to you here is for the y's. So that's 326.6875. So that's what I'm going to use. All right, so the mean of the y's, that was 326.6875. And so I'm rounding it to whatever was in the data here. So the data went to the 10th place because of that data value. So then I'm going to say 326.7, and this refer to grams. So my prediction is that if there is a mammal who weighs 83 kilograms, the brain weight is going to be 326.7 grams. Now remember, I did not have a linear correlation between these two variables. So the best predictor is just the mean of the y's. I cannot use the regression equation to make predictions because the regression equation is only useful if you have a significant linear correlation. And from the very beginning, when we started working with this, from the graph, we already knew we were not going to have a linear correlation or a linear relationship. All right, so this is pretty much all of Chapter 10. We did go through many phases of Chapter 10. So I want to work on, there's one problem that I have for you at the end that I want you to, I'm going to give you some time to work on it. It's just to make sure that you understand the process, okay? So yes, there's a question. And the question says, what if x equals 43? What if we're trying to predict what y equals if x is 43 or something else, right? Your answer will continue to be 326.7, correct. No matter what the value of x is, your prediction is always going to be the mean of the y's. And this is only the case when there's no significant linear correlation. So when there's no significant linear correlation, the best predictor is the mean of the y's. So correct, no matter what the value of x is, y will always be the same. One other thing I forgot to say here is that when you do make predictions, you have to stay within the scope of your data. So it looks like the largest x I had here was 100. So when you make predictions, you can't go above 100 for x. You have to stay within the scope. So 100, and it looks like the smallest is 35. So when you're making predictions, you need to stay within the scope of the data. So nothing smaller than 35, nothing larger than 100. So I couldn't make a prediction. I would not make a prediction for when X is 200 because that's outside the scope of my data. So just keeping that in mind. And so those are the guidelines. That brings us to some of these guidelines. And that's, I was talking about number 2 here. Yes, and what I just said is when you are making predictions, you want to make sure you stay within the scope of your data. So over here, my data goes from 35 to 100 on the X. So nothing smaller than 35 and nothing larger than 100. So if you are making predictions, you need to use values of X that are within the minimum and the maximum. I could not make a prediction for when X is 200 because 200 is outside the scope of my data. Oh, I'm sorry, 27.66? Okay, thank you. So yes, the smallest, I didn't see that. The smallest is not 35, but 27.66. Thank you. So then when I do make a prediction, I need to stay within the scope of my data. So the smallest sample is 27.66. So I could not make a prediction for when X is 200 or when X is 20 because those are outside the scope of my data. So anything between 27, anything that's 27.66 to 100 is okay. We can make predictions for those values of X's. All right, so those are some guidelines. The first one says if there is no linear correlation, you cannot use the regression equation to make predictions. We cannot use the regression equation to make predictions if there's no linear correlation. And a regression equation based on old data is not necessarily valid now. So you need to make sure the data is current. And we're never making predictions about a population that is different from the population from which the sample data were drawn. So the prediction that's being made is based on the sample data that we're looking at. And it's only for that population. Okay, so this is the example that I wanted to finish with today, and I want to give you some time to look at this. And the question here, we want to make a prediction. All right, so that's the background here. We're talking about blood pressure measurements. So we have blood pressure measurements of a single patient. And they were taken by 12 different medical students. So our N is equal to 12 here because we have 12 different measurements. And so there's the first measurement, the second measurement, the third measurement, and so on. So what I want to know is I want to know if there is a linear correlation between the systolic and the diastolic pressure. And if there is a linear correlation, if there is a significant linear correlation, we want to make predictions. All right, so let me go to the next slide, and so that gives you a little better idea. What I have here was just, if you're not sure what the measurements are, that just kind of explains what the measurements are. Up here is just an explanation. When your heart beats, it contracts and pushes blood through the arteries to the rest of your body. And this is the force that creates pressure on the arteries, and this is called the systolic blood pressure. And systolic blood pressure that is 120 or below is considered to be normal. The diastolic blood pressure number, or the bottom number, indicates the pressure in the arteries when the heart rests between beats, and the normal level is 80 or less. So just a little background information about blood pressure. All right, so the questions I'm asking you is, I want you to do a visual inspection. Does there appear to be a linear correlation between the two variables? So a visual inspection means you're going to construct a scatter plot, like we did for our example. Now, if there appears to be a linear relationship, if your scatter plot has a linear pattern to it, and there seems to be a linear correlation between your two variables, then I want you to give me the measurement of that linear relationship. Does anybody remember what gives you the measurement of that linear relationship? What did we call it? What is the strength of the linear relationship? What did we call that measurement? Okay, good. We called it R, so you want to find R. And then the third question says, is there a linear correlation? So we want to see if there's a linear correlation. And so that was a formal hypothesis test. Okay, so is there a linear correlation between the two variables? So you have to go through a process of hypothesis testing. And at the very end, we want to predict. We want to make a prediction. So what would the diastolic measurement be if the systolic measurement is 125? Okay, so go ahead and start by graphing your data. And so the first question I have for you is, does your scatter plot suggest that we have two variables that are related to where a linear relationship exists? Do we have a linear correlation between our two variables? That's my first question. All right, so I'm curious, did you, by looking at your graph, did you get a graph that appears to have a linear correlation between the two variables? Was it better than our example? Okay. All right, so it's going to take you some time to enter the data. So you want to make sure you enter the data just like we did before. All right, so let me go ahead and, if you're still not seeing it, let me go ahead and show you what I have. Okay, so you have to enter your data. So if you go to Stat and then Edit, you enter your data. And so I've already done that. I've entered my data into L1, L2. Then I have to graph it, right? So I'm going to go to second y equals. So if I go to second y equals, my stat plot is already on. So if I enter, it should already be on. I should have it selected for the scatter plot, which is the first graph there. So to select, you just go over it and press enter. Make sure that your x's are in L1 and your y's are in L2. But if they're not, then just make sure you type in the lists that they are in, and then select a mark. Doesn't matter which mark you select. I just like the larger one because I can see it. All right, so once your window is set up, which should be just what it was before, go to Zoom. So Zoom is this button up here. If you go to Zoom, you're looking for, if I go up instead of down, I'll find it. Oh, nope, I didn't. I thought it was the last one. All right, there it is. It is my Zoom stat number 9. That's what I'm looking for. So if you select Zoom stat, it will set your graph so you could see the data we just entered. So it's going to set up your window so we could see the data we entered. So Zoom stat, and there it is. So it's probably closer to a linear correlation than our previous example, right? So as x increases, so does y. It looks like it, right? Now it's not a perfect positive linear correlation. The slope would be positive here because as x increases, y increases as well. It's not a perfect positive correlation, so r is not going to equal 1, but how close is r to 1? All right, so I would say yes. It looks like there is a linear correlation here between the two variables. And so you already have your r. Okay, so the r is going to be rounded to 3 places. So 0.8 sounds about right. Yeah, 0.810. Okay, good. So then after that, you go to Stat, you go over to Tests, and I'm going to go up instead of down because I remember that linear regression t-test was at the very end. So if you press Enter and just make sure that your x's are in the list that you've typed out here, and your y's are on that list. So I have x's in L1s and y's in L2. And just nothing else changes. Just go over the word calculate and press Enter. So the value, so your regression equation is there in case we need it. Our test statistic is there. Our p-value is there. Everything we need will be there. So at the very end, that's the r that you're giving me, right? And you round it to 3 places, so that looks good, 0.810. All right, so let's go ahead and fill out our information on the side. All right, so we did a visual inspection. That was our scatter plot. And so we say, yes, there's definitely looks like there is a linear correlation between the two variables. And so r is equal to 0.810. Okay, so then now you have to go through a hypothesis, a formal hypothesis test. And I'm just going to use method 1 just because of time. So I'm going to set up the null and I'm setting up the alternate. Remember, rho is our parameter. So there's no significant linear correlation if it equals 0, but there is a significant linear correlation if it does not equal to 0. So I would label that at the very beginning. That's our first step. Our second step is our test statistic, and this is the value of t that the calculator gave us. So I believe if I paid attention to when I did the linear regression t-test, I believe it was 4.365, and I'm rounding it to 3 places. That's how we usually rounded our t's. 4.365. Our third step was our p-value. And what I saw for the p-value here, it was 0.0014. That was our p-value. Now, it's definitely less than alpha. Okay, again, I didn't give you an alpha. So what do I use? All right, so now you know we are going to use 0.05. Good. So yes, our p-value is definitely less than alpha. So that means that we are going to reject the null hypothesis. And if we reject the null hypothesis, I am going to put a line through the null hypothesis. We just rejected it. So I'm crossing it out just to remind me that now I believe that there is a significant linear correlation because that's what it says in the H1. So in this case, for step 4, we say there is a significant linear correlation. All right, so for this example, you look at the graph, the scatter plot, and some of you weren't too sure if it was a linear correlation. It sort of looked like one, but we're not sure of the strength of it. So we found R was 0.810, not bad. But we want to find out if it's a significant linear correlation. And it turns out that it is. It is a significant linear correlation. So now when we make predictions, I'm going to just write down my regression equation, just so I have it. It looks like it's negative 1.224 plus 0.699x. So our slope was 0.699, and our y-intercept was negative 1.224. So I have my A and my B, and I put it in where it goes. And that's my regression equation. Can I use my regression equation this time to make predictions? What do you think? All right, so we do have a significant linear correlation. Because we have a significant linear correlation, yes, so finally we can use our regression equation to make predictions. So I just take the 125 and I plug it in for x, and that gives me the value for y. So look at the y values in my table. So I'm just going to keep it to the same place, so it looks like it's 86. Okay, so the best predicted y for when x is 125 is 86. So if your systolic pressure is 125, that means your diastolic pressure is 86. So there seems to be there is a linear correlation between those two variables. Because there is a linear correlation between those two variables, we can use the regression equation to make predictions. And that's what I just did. All right, so that is pretty much chapter 10. Your homework is already up there for you to start it before you forget how we go about determining whether we have a significant linear correlation. All right, so I am printing out the participants list. And I will talk to you next time. So make sure you go to see what homework is up there and what quizzes are up there too. Make sure you check all of your assignments. All right, so I'll talk to you next time.